Okay, so let me recall the place that we stopped this morning. So remember that we are trying to prove the result on which we have this Kenig-Pipher condition, this Carlson condition with sufficiently small constant. So that was the statement. This is proved by contradiction, so one has to be a little careful with the constant. So remember this morning, because I'm proceeding by contradiction, I have this sequence of epsilon going to 0. I have a sequence of bounded one-sided Corner domains, elliptic operators, and they are in infinity, and the constants are all uniform, which is key for the argument. And remember that I move everything to the origin, and I also rescale so that the scale on which things fails is 1. So I know that 0 is on all the boundaries. I know that the diameter is always greater than 1, and I know this is the contrary to the conclusion. I know that this doesn't have an exterior corkscrew, so it means that there is no ball, right? So what I did this morning was there are two cases, and I just decided to focus on one of the cases. So the case in which all these sets are kind of growing to an unbounded domain. And then I remember I defined this function. What I saw this morning is that these functions converge uniformly over compacted to some nice function, which actually has the property that if you look at the level set where these functions are, you look at the level set where the function u infinity is greater than 0. So we know that all the boundaries of the omega j's converges to the boundary of omega infinity. The omega j is the closure, converges to the closure of omega infinity. And these are one-sided Corner domains with control constants. So in the limit, we are getting a domain which essentially has the same properties. Okay, so this is regarding the geometry. So for the moment, I have probably used only this part. I haven't used, and of course this part, but I haven't used neither this nor remember that this is the other condition that I need. So for the moment, I haven't said anything about what is the convergence of the operator or what is the convergence of the matrices. So this is my next goal. For the moment, forget about that picture. This is for later use. Okay, so let's look about the convergence of matrices. Okay, so fix a point in the domain, and let's look at a ball centered at C0 . So this is an interior ball, so because the radius is half of the distance to the boundary. Okay, so remember that this is the boundary of my omega infinity, and because I have this convergence of the boundaries for j large enough, my boundary of omega j should be here, right? So that's somehow the idea. Okay, so in particular, I know that for j large enough, Cj is in the domain omega j, and the distance to the boundary of omega j is comparable to the distance infinity, and I should put here infinity of C0. Okay, so this is this picture. So the distance to omega infinity is comparable to the distance to omega j. All right, so let's look at the integral of aj minus. So by this I mean the average of aj in the ball B0. Okay, so I can use, because this is an interior ball, so this is everything inside the domain, I can use Poincaré's inequality, and I know that this is controlled by the radius of the ball, but the radius of the ball is like delta infinity. Okay. All right, so now what I would like to get is this thing that, remember, this is the Carlson condition, so I have to have gradient of AJ square distance to the boundary. So I'm gonna force this. So I'm gonna use Hölder's inequality to get here a square. So this means I'm gonna pick the measure of B naught to the 1/2, but the radius of B naught is this distance infinity. So I'm gonna have, this is gonna be 1 plus n plus 1 over 2, coming from the Hölder's inequality, and I get this. Okay, and in order to consider this thing that, remember with the star, I need to put a distance to the boundary. So I'm going to put a distance to the boundary, and it doesn't matter if I put delta or delta j, because in this ball, because you are away, the distance to the delta infinity, so the distance to this boundary is comparable to this distance. So I can put this, but I have to pay with the price, because this is all compared, and this is going to be to the 1/2. Okay? This is a constant that depends on C naught, right? This is because this is the price that I pay. And I can now maybe take this ball and put this into a bigger ball, and I can use my Carleson condition. So my Carleson condition is going to tell me that this is of the order of square root of epsilon j, and the surface measure of this ball, which is again the same order. So it's going to be n over 2. Okay? This is a number depending on this distance, which is fixed, but this depends on epsilon j. So this goes to 0. Because remember that my epsilon j were very small. Okay? So essentially this is saying that AJ converges to the average of AJ in B naught in L1 of B naught. Okay, and this is for every point and for every ball that I'm doing. In particular, passing to a subsequence, I also know that this is true almost everywhere in B naught. Right? Passing to a subsequence, I also have this property. So now, on the other, sorry, I put, because it doesn't make any sense, this converges to 0. Okay? But now let's look what it is. This is the average of a matrix over B naught. But the average is a constant, so this is a constant. Right? So this is a constant. And how is this constant? Remember that because I have the ellipticity, this is a bounded constant. This is bounded by the L infinity norm of the coefficient, which is bounded by lambda. So this is a constant, which is a bounded constant. So then, passing to a subsequence, I know that this converges to some thing that I'm going to call A star of B naught as j goes to infinity. Okay? So because I have a constant which is bounded, I know that there is a subsequent which is convergent to this. And this is a constant matrix. Okay. So in particular, using the dominated convergence theorem, I cannot replace this by this. So what I'm obtaining is that AJ converges to A star of B naught in L1 of B naught, and also almost everywhere in B naught, because passing again to a subsequence, I have this property. Okay. So now, but this is true for every. This is true for every ball. So let me erase this. I can cover the whole set by the accountable union of this B case, and for every of these B case, I will have the same property. Right? So I'm going to have something maybe like that. Right? So this is maybe B3 and this is B10. Right? So what happens? What happens is that for any of these, I have a constant matrix, and I know that the matrix converges to right? So this, I'm going to have this limit here, which is A star of B3, and this is A star of B10, right? But this is the same limit of the same AJ, and these are constant matrices. So this means that in here they have to be equal, right? Because there are some points there, and then each of them converges to a constant, but the limit is unique because AJ converges to something, so the limit they have to be the same. So in particular, this says that there is some matrix where I can call, let's define this with respect to the first ball, and because I know that my domain is connected, there is only one, right? If the domain were disconnected, I could have different constant in any of the components. But here, Harnack chain is a stronger version of connectivity. So I can always find from B node that is maybe here, I can always find like a sequence of balls. So at the end of the day, I solve this. Okay? So this is saying that at the end of the day, it's omega infinity, or omega j, if you want. Okay, and this is even true for every p between 1 and infinity. So what this is saying is that locally, A converges to something which is constant. And this is going to be my limiting operator. So now, I define my operator L infinity, which is given by this constant matrix. And then I have the following property. So one can show that L infinity of U infinity is equal to 0 in omega infinity. So U infinity is a solution of the limiting operator. I can show that U infinity is positive in omega infinity. This is the definition of omega infinity. And I can show that U infinity is equal to 0 on the boundary, which is saying that U infinity is a green function for omega infinity and for the operator L infinity with pole at infinity. Okay, so this is the limiting operator. All right. Thus, it's also not difficult to see that once I have these properties, it's not difficult to see that for every function which is continued with compact support, I have this weak convergence of, this is the same as saying that this converges weakly to this. But in particular, this is saying that because this was in an infinity with respect to omega j, this eventually allowed me to show after some computations that omega L infinity converges to A infinity with respect to sigma infinity. Okay, so now let's look at what we have. Let's look at point 4 there. We have a domain which is a one-sided Corner domain. I also have that A star is a constant matrix, and I also know that this is in A infinity. So then I can use the constant case to conclude that omega infinity has exterior corkscrews with constant n0 of the corresponding parameters of, it's going to be the parameter, the m1 of omega infinity, the gamma of L infinity, and the M2 of omega L infinity, right? This is what the theorem, yesterday theorem said, right? So, but remember that I have control over all these parameters, and this was exactly 1/4 over n. Because this is what my assumption. Remember, my assumption is n is equal to 4 times n naught. So this n naught is 1/4 of n. Okay? So I know that this has a stereo corkscrew for this. But this is going to give me a contradiction, because in particular, it says the following. Remember that my 0 is in the boundary of every domain, so in particular is in the boundary of the limiting domain. And now I know that I can take y naught, which is the corkscrew, the exterior corkscrew relative to 0, 1/2. Because I have a exterior corkscrew, so this is going to be a point which is in B0, 1/2 minus omega infinity. Okay? And I have this is with constant n naught. Okay? But now, because of the same reasoning as before, my omega j is here. So this means that omega j has an exterior corkscrew with constant n after. And this is a contradiction. So the same exterior ball that is valid for omega infinity is going to be valid for omega j, because the boundaries are so close, and you have to play with the constants, and then you conclude the same thing. So you reach the contradiction. So remember that the contradiction was there is no ball containing B0, 1 minus omega j of radius 1 over n, which is the same as having not having this ball. And then we are done. Okay? So this, as you see, this is the argument that we have for the small constant case. It's a little bit delicate in terms of the constant, but somehow all these proof by contradiction, they are always delicate, because you don't really show something, you show that something cannot happen. Okay? All right. So in what is left, what I want to show is that how can you obtain from a result that tells you something for a small constant, something for a large constant. And this is something that is called, like extrapolation kind of result. All right, so let me now focus on this. So the theorem says the following. Now I don't care about the constant. The theorem says the following. If I have a one-sided choral domain, I have an elliptic operator, I have that the harmonic matrix is in L infinity. I also need here that this is in L infinity, because that was the Kenig-Pipher condition. So for the class of Kenig-Pipher condition, I can derive that the exterior corkscrew. Okay, so the difference is that I'm putting this because this is a natural condition, and I'm passing from a small constant to an arbitrary large constant. Okay. So how do you pass from a small Carlson to big Carlson? There are already results in the literature about this. For instance, if you look at one of the papers on the Kato conjecture, they also have this kind of this kind of thing. So this is not new. The only thing that is new is in this context. Okay, so I'm going to use what is called extrapolation for Carlson measures. Okay, so my Carlson measures are going to be discrete, so I'm going to put this Carlson condition, this discrete Carlson condition. So the idea is the following. So suppose I'm given a sequence of non-negative numbers indexed by d, and I define the following object. This is a measure over the dyadic cubes induced by alpha. So any set of dyadic cubes, how do I measure this? By using these coefficients. Okay, so what is a Carlson measure with respect to sigma? A discrete Carlson measure even probably I don't need like a localized, or maybe I need a localized version. So this is going to be the Carlson norm with respect to some given cube Q naught, is the sup over L cubes that are dyadic with respect to Q naught. Right, so this is a discrete Carlson measure. Okay, and I'm going to use the notation that M is a Carlson measure where this is finite. So what is the relevant result here? Is the following, says the following. I have two of these discrete sequences. So I have a sequence, one sequence gives me n, another sequence gives me what I call m tilde. Okay? I know that M is a Carlson measure. When I say a Carlson measure, it means that this is regardless of the Q naught. So it's true for every cube. And my goal is to show that this other one is a Carlson measure. So the following suffices. So suppose there is some constant so that the following happens. So first of all, I have that every beta q is controlled by n1 sigma of q. This is some compatibility condition. This is not important. And this is the delicate thing. I need to find epsilon, which is typically small, so that the following occurs. If such that for all q dyadic and for all f qj's pairwise disjoint such that so this is what I need to show in practice. I need to show that I can find some small number so that given any cube and given any family of pairwise disjoint cubes, so that the restriction of M to the family, I will define this in a moment. If this is a small, then I know that this is bounded by M1. Then M tilde is a Carlson measure. Okay, so forget about the one. This is just a technical thing. What this is saying is the following. It suffices to see that this restricted to some subcollection of cubes is Carlson provided this is small. I know that from the logical point of view it's a little bit complicated, but this is the goal. The goal is to say I'm going to need to find something, some very small number, so that if I know for some reason that this is very small, I know for some reason that I can solve this, but only restricted to this. What is MF? It's going to be given by so remember that these cubes appeared yesterday. This is the collection of cubes primes which are not contained in any QJ in the family. This is the same as I said yesterday, stopping time cubes. I have some kind of stopping time cubes, and what I'm saying that this, the restriction of the family alpha to the cubes that are not contained in any QJ is small. Okay, so this is the setting, and this is how I'm going to use this. This is going to be, because I know the result for a small constant, the only thing that I need to know is to discretize this, make it like a discrete Carlson measure, and then because I know that this is small, I am going to show that something is a Carlson measure, and I will be done. So that's somehow the idea. Okay, so this is one of the ingredients, and the second ingredient is the following. If there is a domain satisfying in the exterior corkscrew, and we have, this is Ahlfors regular, the following are equivalent. Partial D is uniformly rectifiable, is equivalent to what is called the CME condition, which is Carlson measure estimate. So this condition says that for every U bounded harmonic, I have this Carlson estimate. Okay, so uniformly rectifiable is equivalent to this property, that every harmonic function which is bounded satisfies this, what is called this Carlson measure estimate, which is similar to what the condition that we have here for the metric, but this is true for every solution. So again, this is a way to connect geometry with the properties of solutions. So this was proof in joint work with Steve Hofmann and Svelana Mayboroda for the point one, for the going down implication, and then the converse was shown by Garnett, Moroglu, and Tolsa. Okay? All right, so I think now I'm ready to give the proof. Okay, so to give the proof, I need to discretize my domain. So given omega, I do a Wigner decomposition. So remember, it's a Wigner decomposition. I decompose the domain in cubes, dyadic cubes, so that the length of the cube is comparable to the distance to the boundary. Okay? I'm going to need to make the cubes a little bit fatter. So this is a disjoint, almost disjoint collection. So the cubes just are close, so they meet on the boundaries. I need to take a flattened version of the cube, so I multiply by same factor, and probably sometimes I'm going to need to even make them fatter. And I'm going to define the following object. So given a Q in the boundary, I'm going to define a Whitney region. What is a Whitney region? It's a union of Whitney boxes on this form. And I need to take the dilation because otherwise I can start creating, for instance, if I have something like that, that will be problematic. So I need to dilate things so that the resulting UQ is connected. And actually, I can make these things to be like a connected domain because of the fatten factor. This is going to depend on tau, but tau is fixed. So sometimes I do this, sometimes I do UQ star, which is the fatten version. And then the only property that I need you to recall is that Whitney cubes have the boundary overlap property. If you dilate them a little bit, you have this thing. And the same occurs with the UQs. Okay, so I can sum and I just lose some dimensional constant. So this is what I'm going to need. And with that in mind, I'm going to be able to discretize all these things. Okay, so what is going to be, in this language, what is going to be my alpha q and my beta q? So alpha q is the one that I know that is a Carlson measure, and beta q is the ones that I want to show that give me a Carlson measure. What is my alpha q? My alpha q is given by the matrix. So I'm going to define alpha q to be so this is going to be my alpha q. So it's the discretization of the condition on the matrix. And this gives me, in that language, the discrete measure M. And what is going to be beta q? Beta q is, so I'm going to fix I can fix a bounded harmonic function. I can assume that it's an infinity because of the homogeneity of the inequality. And by the way, there is a square here that should be here because otherwise this is not homogeneous. Okay? So then I'm assuming this, and this is my beta q. So in the alpha q, I need the fatten version. In the beta q, I don't need the fatten version. All right, so these are the ingredients. So let me finish the proof. So first of all, so let's look at the extrapolation result over there. I'm giving the alpha and giving the beta. I need to know that M is a Carlson measure. So let's check this in a moment. So what is the thing that I need? So I need to compute this. So I need to compute this alpha. So this is this union. Okay. As I said before, these have boundary overlap, so I just can replace this by the union. So let me draw a picture. So what I'm doing is if I take the Q and I start summing all the Whitney regions, what I get is something of this form, which is a Carlson region. And then this is contained in a ball of comparable size. So I can use that this is finite, so I'm going to control this by the star, and then it's going to give me the radius to the power m, so it's going to give me this by using Ahlfors double regularity. So this shows that M is a Carlson measure. Okay? So how do I show the property 1? Is Cacciopoli plus trivial estimates. This is just, at the end of the day, a Carlson measure is much deeper than beta q smaller than this because I really need to sum over all the cubes. So this is just telling me that for the bigger of the coefficients, for the Carlson box, I have the Carlson estimate. But this is exactly Cacciopoli because I have to do this. I know that the distance to the boundary is like the length of Q. And now I can discretize the UQ as a union of boxes. I can use Caccioppoli in every boxes. I can put all the boxes together. So what I get from here is L of Q times from Caccioppoli of Q squared times maybe the flattened version of UQ. And I know that U is bounded by 1. So then I get like 1 here, this measure. I have to the n plus 1. So at the end of the day, I get length of Q to the n, which is sigma of Q. So which is showing that I have 1. Okay, so this is the trivial part. So now to continue, what I need to look is at this thing. I need to look for some small thing, assume that I have some fixed cube, this disjoint collection, and then show that this implies this. And this is what I'm going to do. So the goal is to find gamma small so that so this is what I need to know, what I need to show. Okay, so given epsilon greater than 0, I'm going to find gamma, which depends on epsilon, so that okay, so this is my goal. So what is going to be omega star? Omega star is going to be, because remember what I have here is the union of, what is that? I said somewhere that this MF is the restriction to this thing. So what is my omega star? My omega star is the union of the UQs for cubes that are above the stopping time regime. So let me fix Q naught, and then I take the family F. So this is what I need to do. So what is this doing for you? So I have my family Q1, Q2, Q3. So this is the cube Q naught. So this is doing something like that. So this is the omega star, which is this union of Winding regions. So it's kind of leaving a tent above the QJs. Okay, so this is my thing. So why do I have this? Because this is again the discretization thing, right? If I'm a star, this omega star is the union of this thing. So if I discretize this as the union of the UQs, actually from here I can pass to the sum over the alpha cubes for cubes belonging to df Q naught. And this is what I know that is small. So this is just a very easy trick. So this is just a discretization. But what is the thing that I have now? I have a small matrix, a matrix which has this Carlson condition with a small constant with respect to the omega star. But I have a smallness. And what is the epsilon that I chose? I chose the epsilon related to omega star. So remember that my previous result says that for any domain given some constant, I know that the smallness of the Carlson condition implies a stereo corkscrew. So if I pick the epsilon related to the constants, the one-sided Corral domain constants omega star, which are all controlled by the ones of omega, this is part of the argument, then I know, but the small case, that omega star has exterior corkscrews. Or remember that was the same, that omega star is UR. Okay? So this is the conclusion. The conclusion for this is that, assuming that this is sufficiently small, I don't know it for the domain omega, but at least I have it for this sawtooth. And I need to keep pulling the string. So where do I continue? So this is the first step. So let's look for the second step. I cheated in something because that's not quite true. In order to be able, so I have the Carleson condition there, but remember that my theorem has two ingredients. It's not only having like a small constant, I also need to know that the harmonic measure is in A infinity. So in the process, I need to know that okay, and this should come from omega in A infinity. So this is a delicate argument, and what it's saying is that anytime you have an A infinity, the harmonic measure is in A infinity, which is part of the hypothesis, I can show that for the associated sawtooth domain, this domain that has this kind of shape, I can show A infinity. This uses Kenig-Pipher result, because this is not only about inheriting the property from the domain omega to omega star. At some point, you need to be working in a polyhedral domain. You need to be working in something like that, like a sequence of boxes that meet one particular one. So, and then this is your domain. It's not true in general. It's not true in general that if you have something which is in A infinity, this is inherited. This is the new domain. So this is what we call a polyhedral domain. So if I know that my original harmonic measure or elliptic measure is in A infinity, it's not true that the harmonic measure for P is in A infinity. That's not true. But it is true for the Kenig-Pipher results, for the Kenig-Pipher operator. Because these Kenig-Pipher operators that have these properties, remember that Kenig-Pipher has two things, L infinity, Carleson, they pass to subdomains. So you have something, because the distance to the boundary is in the numerator, if you have something which is in L infinity with respect to a domain, it is true for any subdomain, and you have to change the distance with respect to the subdomain. If you have something using this property and this property, you can actually show that this passes to subdomains. So you have to do some computation, but this is not that difficult. So anyway, so what this is saying is that because I have omega in A infinity, and because I have this property with kind of, you see, there are several cases in which sometimes you inherit the property from omega, but sometimes you need some kind of like a polyhedral domain given by union of Whitney boxes, then I know that I can show this. And this is where I can apply the small case. Okay, so this is part of the proof. And now I'm about to finish. Okay. So remember, by the extrapolation result, what I need to show is that this is finite. So this is what is left. Okay, what is this? So this is the sum over all cubes in here of the beta q's, which are this thing, right? So I can sum all of these using the boundary overlap property, and I have this. Okay, so what is the problem? The problem is the following. Remember, by my omega star, I have this with the star, but I don't want to put the star so far. The problem is that because I know that this is a Corard domain, I can use this result over here with d equal to omega star. So I have this Carlson-Messer condition. So if I will be able to show that this is, and this is the question, if I know that this is true, then I can use this result over here, and I can use the Carlson-Messer condition with the ball that covers the whole domain. So I will pick the L infinity norm that is equal to 1, some constant, and this is, which is the length of the domain, the diameter of the domain to the power n, but this domain has diameter length of q naught. So this will tell me that this is controlled by length of q naught, sigma of q naught to the n. But the question is, well, how do I know this? The problem is that how do I know that the problem is not, remember that omega star is the union of the corresponding UQ star, but the problem with the delta. How do I replace the delta by delta star? Okay, so, and this is what I need to, this is what I have to work with UQ and UQ star. So let's look even in some of these Q stars, right? Or let's look at, this is a union of Whitney boxes, right? This is a UQ. And what is the corresponding UQ star? This is like a fat inversion. Right? So what happens is that if x is in UQ, then delta of x is comparable to delta star of x. Why? Because I have this, my x is in here. What is the distance of this point to the boundary? It's of the order of this length, which is length of q. So this is this thing. This is the length of q. But then, what is the distance of this point to the original, to the omega star boundary? List this thing. But this is with tau or the order on length of q. So this is all the order on length of q. So what happens is that because I'm kind of fattening the cubes, I can replace it by omega star. So I have replaced this by the omega star, and look at what I have shown. I have shown that m tilde of the fq can be controlled by sigma of q naught, and this is the ingredient that I missed in this result, right? So remember that my goal was to say I need to find gamma small enough so that if this is small, this is finite, and this is what I have shown. If this is small, this is finite, and that's the end of the story. So this is the conclusion of the result. Okay, so this extrapolation things from the logical point of view, I know that some is kind of hard to digest, but the philosophy, and this actually happens in several results, the philosophy is that in order to show that something is a Carlson-Messer, you have two Carlson-Messers. One is a Carlson-Messer, and the other one that is the one that you want to show that is a Carlson-Messer. This is telling me, forget about the result, telling me that in order to do that, it suffices to know how to prove the Carlson condition whenever the first one is small. So a priori, the m and m tilde don't talk to each other, but somehow this condition makes the connection. So if I know how to prove that for something small implies that the other one is small, a posteriori I know that the other one is a Carlson-Messer in the whole domain. So the advantage is that I know that this is a small, which is saying good property, because having something that this Carlson condition is very small is a good property. And then the advantage of here is that I don't need to show this in the full domain. I just need to show in the restricted domain. So it's like in this sense what I have, and this is the moral of the story. This is a nice domain, and I have a smallness of this thing. So because I have a smallness of this thing, I have good properties of this nice domain. And because this is a nice domain, I know that gradient of u squared delta star is a Carlson-Messer. I didn't mention that, of course, U to begin with was a solution in the domain omega, but this is a solution in a subdomain. So omega star is a subdomain. So a posteriori know this, and this is what we are using. Okay, and I think I'm gonna stop here. So thank you for your attention.